Okay, so today, what we're going to talk about is like the goal is to continue discussing duality. Just as a reminder, what I was saying last time about the duality stuff. Let's see if I have it here. Um, what we, like the idea is that let's see. Okay, here it is. You know, uh, the idea of the duality was that you have like the ordinary optimization problem that we have worked with and solved using the simplex method, right? The dual is kind of like as closely associated to that original problem, which is usually called the primal, because it controls how big the function that you're trying to maximize can be. Okay. So as I said last time, kind of like the dual, what it does is changes like the matrix with its transpose, uh, then changes like the inequality, because if you see here, like the variables now appear on the right-hand side here, like the variables appear on the left-hand side. And then if it kind of like reverses the roles of like the constant vector with the coefficients vector. And what we had said last time, which was this weak duality, where did I write it? What I said last time was this weak duality that um, what the function that you're minimizing in the dual, it's actually better to just see it here. The function that you're always minimizing in the dual is is always larger or equal to the function you're maximizing in the original problem. Okay, and I'll return to this like next week. But the idea is that there's a stronger version of the duality that says that if the max and the mean are both finite, that's one way to say it. That if the max and the mean are both finite, they actually are the same value. Which in the farmer's problem, that's what we were finding last time. Okay, that's called the strong duality theorem, and it's like an important theorem um, in optimization. Today, what we're going to do, which is not super clear why it would be related to the duality theorem, but I'll make that more precise next time. Today, we're going to do is kind of like an intermediate step, which is like an ingredient in that proof, but in its own right, it's like an interesting thing, which is called the Farkas lemma. So that is what I'll discuss today. So this is going to be the key to proving the duality theorem. And this like lemma already has like some interesting applications. So I'll give you like an example to probability theory actually, like with these Markov chains. Um, okay, so before like telling you what it says, I do have to remind you of how to think about matrix multiplication, because I don't think we have talked about this before. So just like, but you would have discussed this in linear algebra. So just like a quick reminder of like how to interpret matrix multiplication. So I'll just do like a baby example, and then I'll kind of like write in general how this is supposed to work. But if you have a matrix, right, let's say 2, 4, 5 times a vector, right? Let's call this like well, x1, x2, x3, right? So hopefully you remember how to do the products, but what you do to compute the product is you do the dot product between the row and the column vector, right? And that gives you gives you x1 minus 2 x2 plus 3 x3, and then you do the dot product between the second row and the column vector, and that gives you 2x1 plus 4x2 plus 5x3. Right. So that's all good and nice. But that way of like doing the multiplication between the matrix and the vector, what it does is like emphasize the rows of the matrix because you're doing the dot product between the rows and the column vector, right? Um, Now, what's kind of like nice is that there's another way to think about the matrix multiplication, which is kind of like the column interpretation, where essentially let me okay, let me put it like this. Imagine just taking the vector, right? And transposing it so that it becomes like horizontal. So you have x1, x2, x3 here, right? X1, X2, X3. And the idea is that you multiply each of the columns by the corresponding like coefficient. So like another way to do this product is to say that this is X1 times the first column plus X2 times the second column plus X3 times the third column. Is that okay? So just to make it a bit more clear, what I'm saying is that if you have a matrix times a vector, so in A, a matrix times a vector X is x1, a1 plus x2, a2 plus x3, a3 up to xn, an, right? Where here, a1, a2, a3 up to an are the n columns of the matrix. And that is like a very useful way to think about the multiplication between a vector and a matrix, or between a matrix and a vector. But okay, so far so good. Looks like a quick reminder. Now, why is that like nice? Because that gives you like this geometric interpretation for a system of equations, right? So this is like the column interpretation of a system of equations. So when you have a system of equations, ax equals b, right? What does that mean? The system has a solution. The system can be solved whenever B is a linear combination of the columns of A. Whenever. Yeah. So I will give you probably some problems by the end of the week for you to work on because, as I said last time, these topics are a bit more tricky than what we have done before. So it's useful to kind of like, it's less computational, so it is useful to kind of like get practice quick. The others like could wait it and when I was giving you the problems, but like these ones, like they do require like a bit more like immediate feedback because they're more conceptual. So like there are more things that you have to keep in mind for like the problems that we'll be discussing here. Um, so again, like it's just saying that X1. I don't know if you remember like what a linear combination of vectors is. It's just taking like sums of the vectors with some rescalings, right? So you take some vectors, multiply them by scalars, and then add them together. Right, so like a linear combination is just like a weighted sum, like that's how you can think about it, where the weights are, or is another name for saying those coefficients x1, x2, up to xn. Okay. So and then now that we have to talk about this, there was this thing in linear algebra called the column space, which meant that which is a vector space, like the vector space generated by the columns of the matrix. So another way of saying what I just said is that B belongs to the column space of A. So another way of saying this. Is that okay? Is okay? Questions up to this point? Okay, so how does this connect to what the stuff that we have been doing? Okay, so what is the relation to what we have done before? How is this related to? Is this related to our optimization problems? Well, the thing is, like, if you remember, in when we were doing the simplex method, right? When we were solving, like, trying to find the max of the function, after adding slack variables, we would end up with the system of equations, right? Like, in the simplex method, we had like the max of something like this, subject to x greater or equal to 0, and that ax equals b. Where here, when I write it in equation form, I mean that if necessary, you added the extra slack variables so that, you could turn them into equations, right? Here, like, I mean, already including the slack variable so that you could have equations. Like, variables are being included. And so, if you see, like, the conditions that define the polyhedra, right? They do involve a system of equations, right? Um, so this part, right? Because of what we just said, this part means that that B is a linear combination of the columns of A, right? Has to be a linear combination of the columns of A, right? So far, so does that make sense? But you also wanted the variables to be non-negative, right? Uh, and these are the coefficients that appear. Oops, sorry, just to go back for a moment. Like, these are the coefficients that appear in front of, like, each of the vectors, if you look at it like in this perspective. So what you want is, if you put these two together, what you're looking for is a linear combination of the columns of the matrix with positive coefficients. Like, that each coefficient in front of the linear combination is positive, or non-negative, sorry. So but the condition, and I'm about to show you with an animation what I mean. Means the linear combination of the columns should be with positive coefficients or with non-negative coefficients. Sorry. Should use only. Okay, is that making sense? So far, so good. So, these two, the last condition is just saying that B is a linear combination of the columns of A, but the middle condition says that the linear combination must happen with positive weights or like non-negative coefficients. So let me show you with an animation of how that looks like, because it's a bit easier to understand, if you play around with like the. Aha, here you are. So let me share my GeoGebra. Okay, so I'm about to explain what's the deal here. Let's see. Okay, so you have three vectors. So I have three vectors, which are 4, 1, which is this vector that ends at the point B. Okay, I have another one, which is this one C, which ends at negative 3, 1. And then I have another vector, which is 1, 4. So I'll write this on the iPad in a moment, but just imagine that the matrix, I'll put it here so that you can refer to it. So what I'm saying is that I have a matrix with 3 columns. Which would be 4, 1. Then negative 3, 1. And then 1, 4. Okay. Okay, so those are the 3 columns of the matrix. The 3 columns gives you 3 vectors, which are those 3 vectors that you see there in the plane. So far, so good. Does that make sense? So I want to consider linear combinations of those columns. So I want to do combinations which look like x1 times 4, 1 plus x2 times negative 3, 1 plus x3 times 1, 4. Okay, so I'll kind of like show you a little bit of how those combinations look like. So first, what I'll do, but the difference now is that the combinations, the numbers that I put in front of each of the numbers that I put in front of each of the vectors are non-negative. So that's like kind of like the extra condition that you don't have in linear algebra, right? In linear algebra, the variables could always be positive or negative or zero, whatever. Here, like we do want like the variables to be non-negative. So like the combinations are specifically with non-negative numbers. So let me show you how that looks like. Let's see. Okay, so let's see. Okay. So the first one, like imagine, like this is kind of so these 3 sliders that you see here kind of control the weights. So I have initialized them at 0, each of them. So each of them is each vector is being multiplied by 0. So 0, 0, 0. That's why you have the point 0. So that there's like something that says here E, and that is where you start there. Now I'm just going to increase the value for x1 for the first in front of the first vector. So the one that controls the first vector is this number D. So I'm going to increase the value for D. Right? And so as you change the value, as you change the rescaling, right? you just get vectors in the direction of this one, right? Because there's only one that you are changing at a time, right? But the idea is that because the coefficients have to be positive, if the coefficients could be whatever, you would get a line, right? If you allow for negative values, because then it continues in this way. But because the coefficients are non-negative, instead of getting a line, you get you know, you get a ray. Is that making sense? So that is what happens if you were only to change the first coefficient. Now, what if I want to, like, just to do another one, what if I change the coefficient, like the rescaling along the vector that's being called W here, right? Now that's how the rescalings look like in that case, right? Which makes sense. Of course, this continues forever. It's just like I truncated it up to 2. Uh, but kind of like the fun part is like what happens if you do simultaneously, right? So like let's say since we're focused on the first on these and these, let's say I kind of will do each of those rescalings like at the same time. Okay, so you see like these are all the vectors that you can generate by kind of like increasing the weights in the first two. Is that making sense? And I don't so all the vectors that you see there are being obtained from non-negative combinations of vectors 1 and 2, like the ones that are called U and W here. Now, what does that look like geometrically? If you kind of like think about it, that will look like a cone. Okay, so let me see if I can show you that. Is this the first one? Right. Mm, I forgot to do the other ray. Oh, let me insert it as a. Let me stop this because this is kind of like annoying. But stuff saying, yeah, I don't want to select this object. Okay, so then ray of 80. Okay, so just to kind of clarify what I was saying, what I'm saying is that if you just take the first two vectors that you see here, the vectors that you generate, which are these black ones, will always remain between these two lines, between these two rays, and that gives you like, like a cone on the plane. Is that making sense? So instead of like getting a vector space, because if the coefficients could be anything, if these could be positive or negative, you actually would fill out the entire piece of paper. Like, it would be a two-dimensional because it's like two linearly independent vectors. And linear combinations of two linear independent vectors is two-dimensional and you're on the plane. So that will give you the entire XY plane. But because you're restricting yourself to non-negative numbers, you don't generate the entire plane. You just generate like a section of it, which is like this cone. Okay? Is that okay? Is that making sense so far so good? Okay, and just to kind of like, because this is the most important idea of today's class, so it's kind of like useful to kind of like go through it slowly. So for example, what if I had done like combinations of these two, right? Like the middle, the one that's called V and W. So if you do V and W, then now this is how the combinations look for those two, right? So imagine again, like you kind of have to imagine what gets stripped out by just changing the parameters like of the weights. And you see there, like you also get like a cone, but it's a different one, right? Like it's determined by this ray and this other ray. Okay. So by taking like linear combinations of these two vectors with non-negative coefficients, you get a different cone, right? And if you did like the three at the same time, which of course you could do, poor thing, like it depends. Then like the rate, the cone that you get is kind of like the bigger one, right? So it would be this one. Oops, and I am not this one. Yeah, it would be like it would be the one that's determined by these two. Okay. So all that I'm saying is that like the idea pictorially, what you should keep in mind is that when you have vectors and you take their linear combinations with non-negative coefficients, instead of getting a vector space, you get a cone. Okay, that's how you should think about this. Is that making sense? Like questions about that? Is that reasonable?
It's just the, it's the takeaway, just that if the vectors are positive, then it'll just make cones.
Well, not the vector is positive, but the coefficients in front of the vectors. Yeah, as long as the vectors are sorry, as long as the coefficients are not negative, you get a cone. Yes, yes, yes. But it's kind of nice to see it with the animations, you know. It's more plausible to convince yourself about that. Is that okay? So okay, let's go back to the let's end this end. I can upload this to Judge, right? Someone wants to play with it. Oh, I have to, sorry, I have to unplug the cable and put it back in. And so like the interpretation like of, you know, so like the interpretation here is that if the coefficients are non-negative, then you know, x1 a1 plus x2 a2 plus xn up to an generate a cone. A cone instead of a vector subspace. That's what the point. Instead of a vector space. So I'll kind of like, let me just like draw like the pictures that I was drawing on, showing you on GeoGebra. Yes.
So it doesn't generate a vector space like basically because it doesn't carry over like the operations.
Because
Like the code.
oh right, it wouldn't right. The thing is like if you look at the vector space condition, the thing one of the there are two conditions, right? Like that if you add them together, it continues to be inside the vector space, and the scalar fails because the scalar is asked to be positive or negative.
Oh, yes.
Right. It can be only right. It can be any real number, and that's what screws up it messes up the you know the vector space property. Yeah, yeah, yeah.
Okay, thank you.
Yes, and that's why it doesn't sweep out everything. So, but kind of like for example, what I was saying is that yeah, if you had like a vector a1 and a vector a2, right? Then the cone is kind of like in here. This is the cone. This is the cone. Oops. And if you had like say three, like you know, if you, I mean, you could even try to do it something even 3D, like you know, but it's kind. Let me see if I do it in a way that doesn't look super messy. Like, I actually will cheat and draw the cone first. So if you had the cone, sometimes that's easier. You know, you could have something like this. But yeah, maybe here you have a vector again, like a1. Oops. One and another vector a2 here. And I don't know, like maybe I need like a third vector somewhere in there to generate the cone. The point that I want to emphasize is that it's not like a vector space, right? It's kind of like a, you know, cone. Okay. So what does because of this interpretation, what does so here this means that ax equals b with x greater or equal to 0, right? Because remember, like when we were setting up the simplex method, we had a system of equations after adding slack variables together with this non-negativity condition. So what that means is that this, if there's like a feasible solution, right? Like that's where like the feasible solution terminology comes from. That a feasible solution, would words like B to be in the cone generated by the columns of A. So this has a feasible solution. Provided B belongs to the cone generated by the columns of A. So again, like maybe you have three columns, like in the example that I was doing before, you have a column, another column, a third column. This is how the cone looks like in this case. So if B happens to be inside that cone, right? If B belongs to that cone, then this system would have like a feasible solution. So here in this picture, B belongs to the cone of A, of the columns of A. Oops, sorry about that. Of the columns of A. So has feasible solutions. Is that okay? Is that making sense? Okay. And you'll see why this is useful in a moment. The Farkas lemma, which I'm about to write, basically gives you a condition that forces B to be in the cone. Like that's kind of what it will say. When can you guarantee that B is in the cone of the columns, okay, of the matrix? Now, before I say it, I do have to mention something before like in case, just to have like some terminology, which is like how to write the equation of a plane, right? So hope like, like I'll start in 3 dimensions, but hopefully you remember, like if you have a plane like this, and this will all pass through the origin, Um, okay, so like the typical way to write this, if like for example, if you took calc 3, like you would have written something like this, right? Like 2x minus 3y plus 4z equals 0. Like that's kind of like how an equation for a plane looks like. If you want to write it more like in like a linear algebra notation, right? It would have been something like well, the way they would have written this is like something like you could write this as let's see if I try to find like some nice coefficients here. Like you could write this like, well, I'll still write it like the way in which like you would have written this is in calculus, right? You would write ax plus by plus cz equals 0, where a, b, c are certain numbers. And the idea, if you look at the dot product, right, you can use this as a dot product. Right? And the dot product of two vectors is 0 whenever the vectors are perpendicular, right? So that means that this vector ABC has to be perpendicular to any point x, y, z on the plane. And so that vector ABC is called like the normal vector, okay? So this is like a vector perpendicular to the plane. That makes sense? Mhm.
Um. Wait, so why are we finding the normal vector?
Yeah, I'm not fine. No, I've just wanted to remind like the definition of a plane. So in general, if you have more variables, there's kind of like a similar version of a plane, which is called like a hyperplane. So like I wanted to mention like what's the generalization of a plane. So kind of like what I'm saying is that like a line. Okay, so here's one way to think about it. Like a line is something like ax plus by equals 0, just because they're passing all through the origin, like because we're like in linear algebra. A plane is something like ax plus by plus zz equals 0, right? And then if you keep going, of course, you want to improve the notation, right? But then you call that a hyperplane. So a hyperplane is something like, I'll call them like n1, x1, plus n2, x2, plus n3, x3, plus, oh, actually, I don't want to, I don't want to have like, let's see, I don't want to call them n because n is usually the number of variables. So, and A, I'll call, okay, I hate this, but I'll call them B. No, they're not even B because B is being reserved. I'll call them, oh my God, like you run quickly. Let's call them W. Yeah, something like unbiased, you know. It's hard to find sometimes letters, you know. But the point is that it looks like a piece of paper, in like okay, not like a piece of paper, like you know, but kind of like the analog of a piece of paper in higher dimensions. So like a line looks like a line. This looks like a plane. In three you know, when there not where when there's an extra variable, it actually will look more like a cube, and then it kind of keeps growing. But like you know, of course, like you cannot do like very accurate pictures, so you just represent it by this. But the point is that in this case, like, you know, the vector W is like the normal vector. Okay. Is that okay? Is that making sense? Um, so I just wanted to just remind you like that a plane or its generalization is specified by this normal vector. That's all the only reason why I'm mentioning this. So this is because they all pass through the origin. So there's nothing else that you have to say since you want them to go through the origin. So like a hyperplane requires a normal vector, which I guess I'll call W for now. Okay. Okay, and finally, after all this like introduction, I can finally tell you what this Farkas lemma says. So the Farkas lemma says that only two things can happen. One of the two things can happen and not both simultaneously. So and again, next time we'll see why this is a useful lemma. It's not super clear at the moment, but it's actually very convenient. So it says like one of the two options can occur. One of the following options can occur. But not both um, must always occur. Okay, let's put it like this. Must always occur but not both simultaneously, just to clarify. So they're exclusive, like, but not both. Okay, so option one is, and I'll draw the pictures next to each option so that it's clear what's going on. So option one is that AX equals B with X greater equal to 0 has a solution, has a feasible solution. Okay. So what does that mean? This is exactly what we have been discussing so far. If this had a B is a linear combination of the columns, right? But the condition that like the coefficients are non-negative says that B had to be in the cone. So option one is just saying that B is in the cone made out of the columns of A. So I'll kind of copy paste the exact same picture that we had before. So like a more geometric way of saying option one. So option one just says that B belongs to the cone of the columns. So option one is just that. Is that okay? Is that making sense so far so good? So that's one possibility. And what option two says is that what happens if this is not true, right? Because they're supposed to be exclusive. So what would be option two? Okay. Well, so option two says, okay, what if this does not occur? If this does not occur, it means that B is not in the cone, right? So okay, so what happens if B is not in the cone? So maybe it looks like this. Okay, so that is kind of how you would expect B to look like if it's not in the cone of the columns, right? So what the lemma says, like the result says, and in this case, you can kind of separate the cone from the vector by a hyperplane. So the thing is, like, if you ever take more advanced courses in all this optimization stuff, uh, with convexity, which is one of the secret ingredients that makes the theory works, in convexity, sometimes it's useful to know that certain things can be separated. So this is called like a separation theorem. So what this is saying is that you can separate the cone from the vector by a hyperplane, which in this picture, it would just look like a line. Okay, so there's, I'll kind of write it down in a moment. So like, it looks very plausible if you just look at this picture, right? Um, but let's think about this as a hyperplane. So what it's option two says is that if otherwise, if B, or let's put it like this, the vector V, you can find a hyperplane so that the cone is on one side of the hyperplane and the vector B is on the other side, on one side. So in this picture, how would that look like? Okay, so if you think about the vector, if you think of the normal vector being W, right? What does it mean to be on one side? What does that mean? It means, for example, that the angle, imagine everything is two-dimensional, so that it's literally lines and it's easier to understand. That means that the angle, if this is like the normal vector and it looks in this way, that means that the angle between W and B is more than 90 degrees. Is that making sense? Like, we just look at the angle here. And I don't know if you remember how the dot product works. Like, maybe I should write it on the board, but like what is the dot product between two vectors? Like, I should have put this as an aside, but like the dot product of two vectors, like, let me put it here because also what is u dot v? U dot v is like the magnitude, the product of the magnitudes times the cosine of the angle, right? If you remember that the formula of the dot product. So if the angle is obtuse, right? What is an obtuse angle that was more than 90 degrees? So what is cosine of like an angle between 90 and 180? That's negative. If it's in the second quadrant, basically. So that means that one way to say this is that the dot product between the vector W and the vector V should be negative, because that tells you that their angle is more than 90. And I'm almost done. I'm sorry, what were you going to say?
So whole. Like, why is it, I know how the dot product works.
Mhm.
Is the hyperplane like kind of the axis?
Well, it's not necessarily a connection. Like, there's several sorry, I still haven't finished writing that, but there's several there's like the hyperplane would just be in this picture would just be a line, a line, whichever line has a property that the vector is on one side and the cone is on the other side, right? So in this case, like the thing is like let me see if I can make a slightly better like picture here, like just to make a more narrow cone. I think if I do a more narrow cone, I mean they're better. Like, let me draw this a little bit better because they always, all the vectors here start at the origin because we're in linear algebra. So like so kind of like you have this cone, which looks like a triangle in this picture, right? You have this other vector. So I'm like, the only thing that I'm saying is that I can find a line, right? With the property that the cone is on one side of the line and the vector is on the other side of the line, right? So for example, this line would not have worked, right? Because kind of like it goes through the middle of the cone. So like, that's not what you want, right? Like that's why it's called like a separation theorem, because it's kind of like a wall, right? It's kind of like there's a wall that you can put in space. So if you kind of like imagine like a thick wall, which is painted, that you could not see the other side, like the cone is on the other side of the wall and the cone and the vector is on the other side. But like, for example, this one would work, right? Like kind of like like there's more than one option, right? That's fine.
So whatever the hyperplane is, wherever it is, as long as it follows that property of having cone on one side and
Right.
B vector.
That counts as good.
Right, so that would have the dot product be less than 0.
Right, in this case, you can, yes, because you want to choose, so the way you want to choose it is that you can choose it so that kind of like, because they're on separate sides, like, of course, if you had put the normal, if I had, this is kind of like oops, sorry, this is a kind of like a convention, because if you had put like the W pointing this way, then the angle would have been acute, but then the angle with the others would be negative, which is what I haven't finished writing. So their dot products are flipped, right? So the way I drew it in the picture, W with B is negative dot product, but then W with all the vectors in the cone would be positive, and that kind of guarantees that it's acute. Is that making sense? Yeah. Right. It's arbitrary which one is positive or which one is negative, and then and but kind of like one important thing is that and WAI is positive, where AI is like like the vectors that make up the cone, where the AI generates generates the cone. So these are the different columns, so these are like the distinct columns of the matrix, right? So for each column, but that's kind of one way to say this, because again, if the first dot product is negative, that means that it's obtuse. And if all the other dot products are positive, that means that all the angles here are less than 90. So like they kind of like landed on one side on the other side of the hyperplane. Is that making sense? Any other questions about this? Like it is actually something that needs to be proved, but I'm not going to go into that because like not the point. Like the picture I feel is kind of plausible enough, but like, and you'll see in a moment, like that's why I did want to do like an application to kind of like show you that it is an interesting result in the remaining minutes that I have left. But it is a useful way in practice to determine that, again, the way I wrote it is clear that only one option can happen, right? So that's fine. But sometimes like it can be used to show that there's like a feasible solution by showing that this option is impossible, which is why I want to illustrate with this example with probability, because it's really cool. And then next time we will use this lemma to show the duality there, which is a little bit less clear how that works, but basically that would be enough. Okay. Okay, so here's like a very cool application of this result. Let me just say here that this is not unique, right? So the hyperplane is not unique. The hyperplane is not unique. Okay, so here's like a very nice example, or like an application of this result. Hopefully I'll get to finish it, or at least I'll set it up most of it for today. I still have like 25 minutes, so it should be enough. Okay, so here's like the setup. You are like a cell phone company. And there are only two types of consumers or customers in the cell phone market: those with cell phone and those without cell phone. So like that's the only thing that we'll look at. So customers or consumers, however you prefer to call it, with cell phone, and customers without a cell phone. So I'm using the letters S for state, meaning that you can be in neither of the two options, right? Like as a customer, you could either have a cell phone or you don't. So you could be on each state at different points in time, right? Like, you could either, and then to make things more like, and then let's say you have like a number of customers in the market. So like, this is like the total number of customers. Total number of customers. Okay. So here's the condition. After a year, or it could be after a month or after a week, after whatever, like after your favorite unit of time, after 1 year, but let's just work with years. After 1 year, okay. Let's say that 60% of the customers without a cell phone will get one, will buy one, and 20% of the customers with cell phones will get rid of it. Maybe they're waiting to buy a new one or whatever. So you can put whatever hypothesis you want. With a cell phone will sell theirs, or Okay. So now this is the point where you want to draw a diagram to make things a little bit more clear and more tractable. So let's call this like I'll do this diagram, hopefully it makes sense. So these two like circles or nodes, which is how you would call this, represents like this each of the states you could be on, right? So what I'm saying is, what am I saying? That if you, so this is a cell phone and this was no cell phone, right? So cell phone, no cell phone. So 60% of the no cell phone people will get a cell phone, right? So I'll draw an arrow. And percentages, we don't like in mathematics. I will just put it as 0.6, right? Because that way you can interpret as a probability. So with probability 60, like another way of saying is that 60% probability that if you choose a person at random from like these customers without service, that they will buy like a cell phone, okay? And what also does that tell you? That tells you that 40% of the people without cell phone continue to have no cell phone, right? So they kind of like loop around like to their original to their like to the state that they were, like they get stuck there, right? And then of the customers with cell phone, right? 20% decide to get rid of their cell phone. So again, 20% is 0.2 if you look at it as a probability. And that means that 80% stick with their cell phone, right? So 0.8 represents like the number of people, you know, that continue to have a cell phone. Is the diagram clear? Is like making sense, like how to interpret it? Okay, so here's the problem. Like I will work it out and you'll see it's like a very nice thing. So kind of like imagine that, like the size, like the initial number of customers with cell phone and without cell phone, right? How does those these numbers change over time, assuming that they have like the same consumer behavior, so that every single time after every single year, like this same like numbers remain the same. Like so 80% of those with cell phone continue to have a cell phone, and 20% will get rid of it, and so on. So here's like the question. If initially yeah, at least I'll kind of set everything up, and next time I'll tell you how to use Farkas lemma to prove this, what I want to prove. There are N1 customers in state S1 and N2 customers in state S2. How many, after N years, how many people have cell phones and don't have cell phones? So after N years, how many customers are in N1 and how many, sorry, in S1 and how many in S2? So I'll kind of, let me draw this diagram on the board because it's useful to have it around. Okay, so let's try to think if there's like a nice way to work this out. So, but is the problem making sense? Kind of like reasonable, like so let's call this year 0, or like initially, right? So n equals 0, like initially. Oh, then initially you had N1 customers with cell phone, right? And N2 customers without a cell phone. That's assuming that those numbers are known, okay? So that's the initial configuration. That's how the year starts, year 0, okay? Now we wait until the end of the year, right? And what is the situation after the end of the first year, right? What are the numbers here? So, okay. So how many people have cell phones now? So like on this node, you have to analyze how many did you lose and how many did you gain, right? So how many are we losing? We're losing 20% of the customers with cell phone, right? So you have to subtract 20% of N1, right? And you're gaining 60% of the customers without a cell phone, right? So you are adding 0.6 of N2. Is that making sense? Kind of like how I made the calculation. So like imagine like that's why the graphs have a direction, because it's kind of like a flow of people or customers, right? So you're losing 0.2%, 20% of N1, but you're gaining 60% of N2, right? And what happens in the other one? In the other one, so you had N2, right? How many are you gaining? You're gaining 20% from state one, right? So you're gaining plus 2 of N1. But then you lost 60%, right, of the people who were here. So you have to subtract 0.6 of N2. Is that making sense? And notice that they add up to the same, right? N1 plus N2. And if you add these numbers, you get N1 plus N2. Like these cancel because it's conservation of people, right? Like, no one is dying, no one is being born, like, no one left. So if like people are moving like in their market decisions, like it is the same number of people, like that has not changed, right? So far, so good. Now, it is convenient, and I still will work with this in a moment, but it is convenient to like, to introduce some name for this quantity. So I'll call it N1 1 because it's after the first year. And N2 1. So like this number 1, like I'm putting it kind of like in parentheses to kind of like emphasize it's not like an exponent. It's just for me to say, okay, this is like the number of people after 1 year. So if you want, like if you wanted, you could have called like this 1 and 1 0 to kind of emphasize how I'm trying to write this, and N2 0, which means like, oh, this is like kind of like the initial population on each of the states. Okay. I'll just kind of mention something else, and I'll finish this example next time, but I'll let you something to think about if you find the problem interesting, and then you can try to work it out, part of it, because it's kind of cool. So this is after 1 year, right? So like, sorry, this was N equals 1, and then let's say you do the same for the second year, right? So you wait another year, and then you ask what the populations are here. But like again, like our assumption is that it is, like the same percentages are like the percentages are not like varying from year to year. So it's still going to be the case that 80% keep their cell phone and 20% change, get rid of it, and so on, right? So if you were to compute the populations after year 2, it is the exact same formula, but you have just to use like the previous numbers, right? Like the populations immediately preceding it. So is that making sense? Like what I did, like, I'm just saying like, because the behavior does not change, it is the same behavior. So you can just like immediately use like the preceding numbers. This is what people call like a Markov chain, because the state and year 2 only depends on what happened immediately preceding it. Like, it only depends on the previous, like the kind of like one step back before it. Not like, you don't need to remember like the numbers from the very beginning. Like, so for example, at year 10, it only matters what the numbers were at year 9 because of like the repetition condition here. So this is what's known as a Markov chain, okay? But the question is, can you find like a useful, a useful representation for these formulas? And you can if you use linear algebra. So I'll let you to think about this because it's kind of like a good exercise for you to work on if you are interested. If you're not, I'll tell what the solution is next time. But I'll kind of like spell most of it for you to work it out. So I'll tell you about this next time. So if you want to find like a useful in order to interpret this better, what you should do, you don't want to, if you kind of keep track of the particular numbers, you kind of, it's too messy. So you call this strategically, I'll call this P12, because this is the probability that someone in state 1 jumps to state 2, right? Then I'll call this P22, okay? Because this is the probability that someone in state 2 goes to state 2, which is another way of saying that you just stuck where you were. I'll call this P21, because this is the probability that someone at state 2 went to state 1. And I'll call this one P11, because it's the probability of being in 1 and remaining at 1. Okay, so if you kind of notice this, the notation is Pij is like the probability for jumping or like switching from state I to state J. From going from state I. Okay. The goal, and notice here something. So you can define a probability matrix, which I'll call this P11, P22, okay? The only thing that's not clear is like the convention here, but this is P12 and this is P21. So this kind of works opposite of like how you usually would write this, because like usually this is like, row column. So like the indices are messed up, but like, it's traditional in this probability stuff to kind of like write it this way. So like notice like notice like the notation of the indices are kind of like a bit like off from like the usual one. Notice that it is different notation for the indices. Okay. The nice thing, if you write it this way, is that the columns, right? What do these columns add up to? Like the numbers on these columns? P11 plus P12, that's, you either go to 1 or go to 2. So that should add up to 1. So this adds to 1. And this other column adds to 1. So these are columns, probability vector columns, because like their entries add up to 1 and each entry is non-negative. So this is what's called like a stochastic matrix, a stochastic column matrix. But try to find a formula using this matrix P and the vector. So try to use matrix multiplication. And I'll kind of say the answer about it, but it's like a fun exercise. I think some of you may want to try it. Try to use matrix multiplication and the vector and let's call this vector n1 and 2 to find okay, so what I'm trying to say is that all these expressions that I had for like, again, this is kind of like the numbers after m years, like let's call it t actually. Let's just to not make it too bad. After t years, so t could be 1 year, 2 years, 3 years. There's like a way to find these numbers in terms of the matrix, the probability matrix that I just wrote, and this like factor n1 and 2. So if you work it out for like the first two cases that we have the explicit formulas for those two. Try to rewrite them using matrix multiplication, and you'll find like a very nice pattern. Okay, so I'll kind of like mention next time how you do that. And then I'll mention how this is all related to Farkas lemma. Obviously, there's some connection, but it's kind of still very hidden. But it's like an interesting problem to like, it's like a cute problem to, if you like probability. So let's finish here, and then, yeah, I'll continue talking about this like on Monday.